and welcome to lesson 4b. What we're going to be doing for the next few minutes is going really slowly through the equations that tell us about gravitational field strength and gravitational potential. And we're going to make sure we know exactly what we mean by all of them so that we don't get confused, because it's really easy to get confused. The first place everyone always messes up is little m, big M, little r, and big R, which is fine. They're really fiddly, and it's always very easy to get them the wrong way around. So, big M is mass of planet. I say planet because 99 times out of 100 we'll be calculating gravitational field strengths around planets. Obviously in your exam they can throw anything at you. It could be around a planetoid, it could be just a proton floating in an empty universe. But in general, this M is the mass of the planet. It's the mass of the thing that's giving out the field. So whatever it is that's generating the gravitational field, that's the M we're talking about. Little m is whatever mass you are looking at inside the field. So I'm looking at my mass inside the Earth's gravitational field. I'll be the little m, and this will be the mass of the Earth. So the m is mass of the thing that you're looking at. So whatever it is that you care about. Yeah? Similarly, big R is the radius of the planet. So when you are at big R, you are on the surface of the planet. That's how it's defined. Whereas little r is how far you are from the centre of mass. So when r equals 0, you're actually at the core of the Earth. When r equals big R, you've got to the surface of the Earth. And when r is greater than big R, you've gone beyond the surface of the Earth and you're off into space. So big R and big M are set numbers which do not change for a given question. So if you're talking about the Earth, they are just facts about the Earth. Little m depends on what you're looking at. Maybe that's the mass of a satellite, the mass of a ball, the mass of whatever. And little r is how far you are from the centre of mass, the centre of the Earth. So that will, if you're in a rocket and you're blasting up into space, your little r will just keep getting bigger and bigger and bigger, whereas big R is going to be set. It's whatever the radius of the planet is. So make sure you never get these mixed up. So now let's look at the 5 equations that we need to understand if we're to really understand gravitational fields. The first one just tells you how gravitational field strength is defined, and it's simply the force per unit mass. So that's little m, it's the mass of the thing. So if you told me that there were 100 newtons of force on a 10 kilogram object, I'd do G is 100 divided by 10 equals 10 newtons per kilogram, and that's just the gravitational field strength at that point. It's just how we define it. If I say, what's the G on Earth, you'd say it's 9.8 newtons per kilogram. Force divided by mass. Simple. What's the G on the Moon? Oh, it's about 1.6 newtons per kilogram. Force divided by mass. However, you might want to say, well, what is the gravitational field strength a kilometre away from the Earth? And it turns out we can work that out. All we do is we say the gravitational field strength is equal to minus gravitational constant times big M, mass of the Earth, divided by distance from the centre of the Earth squared. Now if we're talking about big distances, we can just take it from the surface of the Earth because there isn't going to be much difference there. But over small distances, just be careful, this is distance from the centre, not distance from the surface. So this equation here lets you work out the value of G at a given point. If you then wanted to work out the force on an object, you take this and whack it into here, you already know the M, and that would give you the force. So we use this to calculate the value of G at a specific point, this to calculate the force on a mass once we know the G. So that's what the 2 equations are used for. Note this is little m, this is big M. Now we've got 3 equations that tell us about potential. The first is really simple. The amount of work we do is just equal to the mass times the change in potential. So, if we were at our minus 50 here, and we're going to minus 25, and we've got 2 kilograms, we're moving from here to here, we know it's going to have minus 100 here, because it's 2 kilograms times minus 50, so it's minus 100. We're moving to minus 50, 2 times 25, so our work done is simply going to be 50 joules. It will take 50 joules to move 2 kilograms from here to here. So that's all this equation is telling you. Simple as that. These two tell us about the potential at a given point. This one we talked about in the last video. Our gravitational field strength is just equal to our change in potential divided by our change in distance. And remember, need a cheeky minus on there, very easy to forget. This one is the analogue of this one. This one allows us to calculate the gravitational field strength at a point. This one allows us to calculate the potential at a point. And notice they're exactly the same, except this is r and this is r squared, which would make sense because if one were to differentiate this and whack a minus in front of it, one would get this. Please prove in your own time. So this allows us to calculate the potential at a point. If we then wanted to work out how much energy we would need, we can just whack it into this one. And if we want to work out how much potential something just has at a point, we can just take this and multiply it by little m. And this is just another way of calculating the field strength, same as this. So these two are just two different ways of doing the same thing. This allows us to calculate the potential at a point, gravitational field strength at a point, force on an object, how much work you did moving a mass through a gravitational field. Right, there's a question that requires you to think clearly about potential under this. I want you to have a go, and in the next video I'll show you how it's done.